Tabular data are ubiquitous across industries, but they often contain missing values due to human error, privacy considerations, or data collection challenges. Data imputation is a promising solution to estimate missing values based on observed data. Existing methods use statistical algorithms, shallow machine learning algorithms, and deep neural networks, with deep generative model-based imputation models exhibiting competitive performance. Diffusion models, a leading deep generative model, have shown remarkable capabilities in generating data across diverse types, but their application to tabular data imputation is suboptimal due to two key mismatches: objective mismatch and datascale mismatch. The objective mismatch arises from the inherent difference in learning objectives between generation and imputation problems. Diffusion models are sensitive to initial noise, which helps generate diverse samples but hurts accuracy in imputation tasks. The datascale mismatch occurs because tabular data have a much smaller scale compared to other domains, making it difficult for diffusion models to capture the data manifold and resulting in overfitting. To address these challenges, we propose an advanced diffusion model called Self-Supervised Imputation Diffusion Model, SimpDM. SimpDM integrates self-supervised learning techniques into tabular diffusion models, introducing a self-supervised alignment mechanism to regularize the output and provide consistent and accurate imputation. Additionally, we introduce state-dependent augmentation, a perturbation-based data augmentation strategy that extends the training set and improves the robustness of the diffusion model. Our contributions are threefold: identifying the challenges that hinder diffusion models in solving tabular data imputation tasks, proposing a novel diffusion model that addresses these challenges, and conducting extensive experiments on 17 benchmark datasets across multiple missing scenarios. The empirical results highlight the strong imputation performance of SimpDM compared to state-of-the-art methods. The motivating experiments in Figure 1 demonstrate the issues with vanilla diffusion models. Figure 1a shows that given identical observations, the vanilla diffusion model generates diverse imputed values, leading to significant gaps between imputed values and the ground truth. Figure 1b shows that the limited data samples lead to poor imputation results and unstable performance. We also review related research directions, including tabular missing data imputation in diffusion models. Existing methods use statistical algorithms, shallow machine learning methods, and deep neural networks, with generative model-based approaches standing out for their remarkable performance. The paper introduces SimpDM, a self-supervision improved diffusion model for tabular data imputation. It begins by defining the problem of tabular data imputation and explains the importance of using a hybrid input data design that combines observed entries with initialized or estimated values for missing entries. The model uses a simple MLP architecture with learnable embedding of diffusion steps and missing mask as input conditions to discern the status of the hybrid input. The paper also discusses the pseudomissing training strategy, which involves padding missing entries with column-wise average values during training, sampling pseudomissing masks, and adding Gaussian noise to entries where the condition mask equals 1. This strategy allows the model to be trained by denoising pseudomissing entries since their ground truth values are accessible. The value prediction and loss calculation are discussed, where the model directly predicts the missing values and calculates the loss on pseudomissing terms. The training process of the Gaussian diffusion model for tabular data imputation is expressed, with the loss function focusing on the pseudomissing terms to guide the model towards completing the missing data. In addition, the paper highlights the use of state-dependent self-supervised alignment and data augmentation techniques in SimpDM. The overall training pipeline of SimpDM is demonstrated in Figure 2, which includes applying average padding for missing entries, sampling pseudo and condition masks, and using a self-supervised alignment loss to minimize the distance of predictions at two channels. The model is further extended to handle mixed-type tabular data by incorporating both Gaussian and multinomial diffusion models. The paper concludes by discussing the inference time, where missing entries are initialized by sampling from the final step of the forward process, and the condition mask is set directly as the missing mask. The paper demonstrates the potential of diffusion models in tabular data imputation tasks, providing a comprehensive methodology for enhancing these models through self-supervision. Here is a combined summary of pages 5 and 6 of the research paper. The authors propose SimpDM, a novel diffusion model for tabular data imputation that addresses the limitations of existing methods. They introduce a self-supervised alignment mechanism to suppress the sensitivity of diffusion models to diverse noisy inputs. This mechanism involves constructing two parallel channels with shared pseudo-masks and condition masks, sampling different diffusion steps and noises, and minimizing the difference between the outputs of the two channels with a self-supervised alignment loss. Additionally, the authors propose a state-dependent data augmentation strategy, which perturbs entries in different states, ground truth, pseudo-missing, and missing, with varying strengths. This strategy can generate more reliable training samples and boost the robustness of the diffusion model. The authors also extend SimpDM to mixed-type data by introducing multinomial diffusion processes for categorical features and using random state transformation as perturbation. They evaluate the performance of SimpDM on 17 real-world datasets across various domains and compare it with 11 baseline methods, including shallow, deep, and deep generative methods. The experimental results show that SimpDM outperforms all baseline methods in terms of root mean squared error, RMSE, achieving an average rank of 1.4. The authors also provide implementation details, including hyperparameter tuning, and make the source code of SimpDM publicly available. Overall, SimpDM is a promising approach for tabular data imputation that can effectively handle mixed-type data and missing values. In this research, we introduce a novel variant of diffusion models, named SimpDM, which is specifically designed for tabular data imputation. To enhance the imputation capabilities of the diffusion model, we propose a self-supervised alignment mechanism and a state-dependent augmentation strategy. The self-supervised alignment mechanism aims to eliminate the unexpected diversity of imputation results by aligning the imputation results of two channels. The state-dependent augmentation strategy perturbs each entry in the dataset based on its state and certainty, leading to improved performance in both missing at random (MAR) and missing not at random (MNAR) scenarios. We conduct experiments on 17 datasets and compare our approach with 11 state-of-the-art baselines. The results demonstrate that SimpDM consistently outperforms all the baselines on 11 datasets and achieves runner-up results on the rest 6 datasets. This consistent superiority across a majority of datasets highlights the adaptability and robustness of our method in addressing missing data imputation challenges. To further explore the effectiveness of our approach, we perform ablation studies for the key components, self-supervised losses, and augmentation strategies. The results show that both self-supervised alignment and state-dependent augmentation yield substantial performance enhancements for the base model. Among the self-supervised alignment losses, the mean squared error (MSE) loss attains the optimal results on 7 out of 8 datasets and exhibits competitive performance on the remaining 1. State-dependent augmentation also brings improvement, demonstrating the effectiveness of this strategy. We also analyze the runtime of each training epoch of SimpDM on different datasets. The results illustrate that the training time of SimpDM exhibits a linear relationship with both the number of samples and the number of dimensions, aligning seamlessly with our analysis detailed in the paper. Additionally, the training cost of SimpDM is quite small, indicating the high running efficiency and scalability of our method. Finally, we perform a case study and visualization experiments to investigate whether SimpDM can deliver stable imputation results from diverse initial noises. The results suggest that SimpDM yields both increased stability and enhanced accuracy, attributed to the integration of the self-supervised alignment mechanism. Furthermore, the visualization of the original iris dataset and the data imputed by the base model in SimpDM using the TSNE algorithm shows that SimpDM adeptly captures the data manifold, while the base diffusion model struggles to match the data distribution. Here is the combined summary of pages 9 and 10. The paper presents SimpDM, a self-supervised diffusion model for tabular data imputation. The model aims to reduce sensitivity to noise and improve the stability of imputation results. The training algorithm of SimpDM involves sampling a pseudo-mask, running the diffusion model on 2 channels, and calculating the self-supervised alignment loss. The inference algorithm initializes the input with random Gaussian noise and recursively runs the denoising iteration with the diffusion model. The time complexity of SimpDM is analyzed, and it is shown to scale linearly with both the number of samples and dimensions. The model is evaluated on 17 datasets from the UCI machine learning repository and Kaggle, and the statistics of the datasets are provided. The paper also provides a comprehensive review of related work in the field of diffusion models, imputation, and synthetic data generation. The references cover a range of topics, including personalized risk scoring, generating synthetic data in finance, UCI machine learning repository, perturbation learning, contrastive learning, and denoising diffusion probabilistic models. The authors highlight the contributions of their work, including the development of a self-supervised alignment mechanism and a state-dependent augmentation strategy. They also discuss the limitations of their approach and potential future work, including exploring more complex self-supervised alignment losses and applying SimpDM to more challenging datasets. Overall, the paper presents a novel approach to tabular data imputation using diffusion models and provides a thorough review of related work in the field.